Alright, hell yeah. So what we have here is the rotating disk question from the JEE Advanced. This is the 2016, this is in paper 2. And so they were given credit to an answer that I'm going to say is wrong. We have a center of mass, this is 4m, this is 1m, so it's very close to this 4m disk. And they're going to say the angular momentum, so the angular momentum about the center of mass, about the point that is the center of mass, is going to be basically just the spin component this direction. But they don't take into the consideration that if you look from above, you know what I mean? Let's say, and you can think of this, this is one way to actually prove it. Let's say you were looking at this system from the stars, and you couldn't even gauge this distance from the z-axis. You were so far away that all you could see was like this was a red light and this was a blue light. But you could determine whether this red light was on that side and this blue light was on that side. So within about a minute, I'm actually proving this right now. This is probably the best way. And you're so far away from the stars, all you can determine is red is on this side, blue is on this side. When this thing progresses to the other side, the blue light will be over here, and then the red light will be over here. And then you're going to be able to calculate that. And you know that the red light is associated with a mass of 4m, and the blue light is associated with a mass of 1m. And what you're seeing is that every half a rotation, they switch directions. And once they actually get back where the red and blue are on the same side, you know that angular speed. And that angular speed is just omega divided by 5 from the problem. That's actually just the center of mass of the assembly rotates about the z-axis with an angular speed of omega divided by 5. And because these roll without slip, the quick answer to that is this radius is proportional to this radius. This angular speed is proportional to this disk's radius, and because this disk goes around a circle with the radius of this, and it's inversely proportional. This is 5a, this is 1a, and so the angular speed is going to be 1/5 of the angular speed of these disks. This is 10a, this is 2a. So it's an inverse relationship there. Okay, but hell yeah. But when it comes down to, you know that, hey, from a distance from the stars, you know that the center of mass is somewhere in between these two disks. And then you see that these disks are rotating. Those masses are rotating. So every one full precession, these masses rotate. And that's part of angular momentum. You know what I mean? Angular momentum from like if you could get angular momentum to go to 0, you actually have to stop spin. You know what I mean? And you have to stop spin by using a torque. You can't just stop spin by using, like one force in the normal direction, of the system. Hell yeah. You would have to use a couple of forces, and you'd actually have to apply a couple. You'd have to apply a net torque to the system. Okay, so that's kind of maybe a pretty good start of being like, oh, okay. And then in general, this thing, from a upstairs view, this thing is going to rotate about the center of mass every time it spins around. So if your fixed position is above the center of mass always, you're going to notice that rotation. And to stop that rotation, you would have to stop, you would have to apply a torque on the system that stops that rotation. Hell yeah. Okay, and so now we're going to go in kind of part 2 of this. One thing that you can do with this system is we're just going to simplify it. We're just going to turn this mass into a mass of 1, and then we're going to turn this mass also into a mass of 1. We're going to have a generic distance there of 1 and a generic distance there of 1. And then this thing is going to spin about the z-axis. We're going to take its rotation, and we're just going to, this rotation, we're going to go to 0 on that. But this thing is still going to spin around. So let's say it's on a string. And we're even going to simplify it farther. And so what we'll do is we're going to go out this distance, go out another distance, put the center of mass, and then go out this distance. And so, again, these are just masses of 1. These distances are 1. And what we're going to do is we're going to have... oh, I forgot what we're going to do. Oh, let's see what we're going to do. Oh, yeah. So just in general, if you want, and this is the center of mass, if you were trying to find the component of the center of mass, what you would do is you would take this I, which is the mass moment of inertia, times omega, and this is your vector. You know what I mean? And so, but what's the, like, what is the omega of this? And again, you would have to look very far away. If this thing spins around this point, you know what I mean? If you have this, and then here's your center point, and here's your two masses, and you're just looking from above, and you actually just, every time you move this, and we're focused on the center of mass right here. And so if we do go up here, the center of mass is still right there. But let's start this experiment with the center. So here's our fixed point. Here's our two masses, and we're in our center of mass. This is our center of mass point, and this is where we're going to take the angular momentum. And let's say we do rotate up a quarter. Our new center of mass is right here, but we're going to translate that back to here. So once we spin a quarter turn, these two masses are now oriented like this. So we're going to come back down here. And now let's go back to the starting position. We started from there and we went to there. Let's rotate all the way over here. This is, you know what I mean, from our previous scenario. This is the blue light, this is the red light. And then so the blue light's here, the red light's there, and then the center of mass. So after a half of rotation of this system, these do this. They switch places. So red light here, blue light here, and then red light's now over here, blue light's over there. So this is just showing, kind of proving that if you do have this system will be rotating. Because it's kind of fascinating, and this will be probably just kind of like I'll do multiple parts on this, but this is just the first part, is that this equation always applies, even if it's not obvious that the center of mass is rotating. You know what I mean? But this is the equation of angular momentum about the center of mass of a system, because this system is also translating through space. You know what I mean? Let's say this system was just a mass right here, and it was moving right through there. Well, the mass is moving in that direction. The center of mass is right there. Angular momentum is r crossed mass times velocity. The velocity does have a vector. The distance from the center of mass to itself is 0. You know what I mean? So you would have zero angular momentum of a single mass, calculating, there's the center of mass, you don't have any. And so this system can still be squashed down. I could have 2m here, and I can represent this system as 2m right there, and then still swinging around. The only difference between this is that these two masses will actually switch places along their way. And an angular momentum is, yeah, let's see. Oh, yeah, and the huge part about this, if I stop this angular momentum, what's going to happen? And let's say this actually isn't connected. let's say this just somehow goes through space just like our disks. Our disks have some sort of friction here, rolling without slipping. So now you got to kind of use your imagination. But let's say these just go in a circle somehow because they're in tracks. There's sure friction to keep them in tracks because the center of mass is, going in a circle like that, and we don't, and we eliminated any tension right there. So it's very much like our rotating disks. But the question is still, now I'm just saying words, so let's get back on track. I'm going to drink some water. All right, hell yeah. This one, let's say it also was just rolling in a track or something. The angular momentum about the center. All right, hell yeah, new battery. And I think I know where I want to go with this. So we eliminated the string, but we're still having this on a circular path. This didn't have any angular momentum about its center of mass. That means if you are a person at the center of mass, this doesn't have any angular momentum, so its angular momentum is 0. If it did, so you can't reduce the number 0 to a more 0 number. You know what I mean? So if you got rid of the angular momentum, well, there wasn't any to begin with, and so no change in this system will happen, and it'll still continue to go around. Now this one is a different case. If you're here between these at the center of mass, and you see this system go around in the circle, we are saying that it has angular momentum. So from this perspective, we can say what happens if we reduce angular momentum about the center of mass to 0. If we get this to 0, then what does it look like? What it says is that this center of mass will still go around the circle, right? Just like this one was going to go around the circle. But what happens is that these, which were doing this, and rotating at the same time, that stops. So when this did do that, to get rid of the angular momentum, once this center of mass does go up to that point, up to this point, it just means that these stay in the same position. So that is angular momentum about the center of mass. And so here's another way to look at it. If I'm taking angular momentum about this point, what I'm gonna do is I'm gonna try to observe mass and then look at if it's moving, if it has velocity. And then I'm gonna see if that velocity has a perpendicular component to where I'm looking. So if I'm right here, I'm gonna look over here. Hell yeah. This has a velocity in that direction. And then cool. And, if it is spinning about this point, then, and we say this has a, now let's pick, we got to pick some sort of velocity here. Let's say this is a velocity of 2, and then this is a tangential velocity of 1, and then this is a distance of 1, and let's say this whole system rotates with an angular momentum of 1 radian per second. And, so this is a distance of 1, can be meters or whatever. But then, if this whole system rotates together with an angular velocity of 1 radian per second, that means that the tangential velocity here, I always like to do this, tangential velocity is, let's say radians is confusing. So something confusing times radius is something normal. That's how I like to do it. So radians times radius is something normal. That's tangential velocity. For this, radians is just 1. Radius is 1. So we have a velocity here of 1, a velocity here of 2, and a velocity here of 3. Okay, so let's go back to this angular momentum about the center of mass. We're here. We have observed a mass, there's perpendicular, and so we're going to have a distance out to that mass of 1. So we have, and I'll say distance, mass, velocity. And we got 2 of them, so I'm going to go distance, mass, velocity. So over here I have a distance of 1, a mass of 1, and a velocity of 3. Distance of 1, mass of 1, a velocity of 3. Let's go this direction. I have a distance of 1. And we have to have, this is some sort of vector. Even if we're just in planar space, it has to be either positive or negative. And so let's use the right-hand rule. I'm going to go from here over to that mass, curl my fingers up in the, using right-hand rule. So we're going to be a positive. So out of the page, let's say this is the z-axis, out of the page is positive, but I'm going to have a positive right here. Now this direction, I'm going to be negative. And so I have this direction is 1, and then the velocity is going to be 1 that direction. So we have, this is going to be negative, distance of 1, mass of 1, velocity of 1. So we have 3 minus 1, so this is a total of 2. The angular momentum about the center of mass is 2. Now typically the equation for the angular momentum about the center of mass is just I omega. And so if we come here, what is I when we're here? Well, I is also, what the hell is that? It's observing a mass and determining its distance squared away from where you are. And, hell yeah. And that's in an absolute sense, too. That's, don't quote me on that, but yes, as in an absolute radial sense from that position, this is that quantity. Alright, so let's do it. So if I go from here to there, my distance is 1, 1 squared is 1, and the mass is 1. And then if I go this direction, the distance is 1, 1 squared is 1, mass is 1. So this is going to be 2. So I have 2 for that. And then the omega for the system is 1. So I have 2 times 1, which is the same number as 2. So then we kind of did it in 2 different ways to be like, if I'm at the center of mass, and if I'm at this point and I'm observing these masses go in those directions. So even just for an instant, this point doesn't have to have some sort of traveling velocity when calculating this. It's just a point in space, and then you're observing mass, and you're observing the perpendicular relationship away from those masses. And then, at a split second later, you can regroup and say, well, there again is the center of mass, and I'm looking at these velocities. This one's 3, this one's 1. And so I think that's the more intuitive way, because definitionally, angular momentum is observing some sort of mass. It's some sort of distance to some sort of mass that has a velocity. So here's your momentum, mass times velocity, and then here's your distance. It's a vector because it's only the perpendicular components that are perpendicular with this velocity. This velocity, this distance, and this velocity. It's only the perpendicular components between the distance to that mass and the actual velocity. Okay, hell yeah. But we have observed in this statement that we do have angular momentum because these things rotate. Because this thing processes, every time that it processes once, this whole system rotates one time and then kind of resets. And because if you're at the center of mass and you had to get that to go to 0, you would have to stop that rotation. The thing could still rotate around here, but the way that I thought you would do that is you would have this would be on a bigger table. Let's say this is just on a table rolling around a table, and then on this table it's like a lazy Susan, and then someone is actually so if this thing's spinning this way, someone is rotating this lazy Susan by omega divided by 5. So therefore, this thing is going to translate kind of back and forth, but if you were observing this now from this lazy Susan, you would just see this system. Alright, hell yeah. You would just see this system like move lateral. I think you would just see it move one way and then the other. There's a potential that you could actually have this on a swivel and then actually swivel it where this stays in place. I actually tried to do a drill on this with a golf ball, and then when you actually did that lazy, if this was your lazy Susan, but the lazy Susan also moved in the same or opposite direction as the center of mass moves, you can see this stationary just flipping. And I did that with SpongeBob attached to a golf ball, and SpongeBob would go upside, SpongeBob would rotate in a 360. Whatever direction you pick, SpongeBob would go upside down, and then right side up, upside down, right side up. Okay, hell yeah. So we're basically done with this. I think in kind of like the 30-second... I don't know if I could ever do this, right at the beginning. I'm going to try. I'm going to end this video with saying, hey, this is wrong and why. And I'm going to use a stick example. Alright, well, I don't even know if I have that in my mind yet. Alright, hell yeah. So we go into this problem with some detail. But with under a minute, I think, I can explain kind of what we're doing. The angular momentum about the center of mass was given credit for this answer, which was only the spin component about this axis, which goes to the center of mass. But what it doesn't take into consideration that this thing spins every time it processes. Let's say this is the center of mass, this is the bigger mass, this is the littler mass. What you would look at from above is that you would see it would spin one time. Even though it's like doing something like this, which it's harder to see that it spun one time. The second it gets to over there, center of mass, the bigger mass is now on that side. After it spins around, the bigger mass is on that side. And so in this video, I'm going to show that if you didn't have angular momentum due to that procession, I don't know if you call it procession, just going around the z-axis, this thing would have to look like this. If this traveled around the z-axis like this, you would have no angular momentum. But because it doesn't, any positions, you're going to take this, what it actually does, and you're just going to fix the axis. You don't have to show this motion. You can just show an overhead view of the center of mass, and what you'll see is that it just rotates around that center. And that is picking up a component of spin. It's not orbit. It's just spinning about its own center of mass. It's just spinning horizontally. And so that horizontal component has a positive z component. This has a 20% in the negative z component almost, and then a negative I component, let's say. And so to figure out the total angular momentum, you have to use angular momentum as a vector product is I omega. I is a scalar, but this omega is a vector. And so we have the horizontal vector of its, which is omega divided by 5. So we have omega divided by 5 in the k-hat direction. That's the speed that this thing rotates all the way around one full time. And then we have this omega, which has two components. Mainly it's going to be in the negative, so you have about 98% of that, or 0.98 of this omega is the negative I hat, and then you're going to have a negative z hat component, which is about 20%, just based on the geometry here. You have almost a 1 to 5. Hell yeah! All right, so there you go. So that's, and then we're going to start the video. But yeah, I just wanted to show, this is kind of my first video on proving that this answer is wrong. All right, hell yeah.